We have all had the experience of coasting on a bicycle. If you stop pedaling, you slowly glide to a halt. Based on everyday life, it is perfectly logical to ask, why do moving things always seem to stop? For thousands of years, people agreed with the ancient philosopher Aristotle. He believed that the natural state of every object in the universe was simply to rest. If you leave something alone, it stops. This diagram shows an experiment by Galileo that challenged that idea. By rolling objects on smooth ramps, he realized that earthly objects don't naturally want to stop. They are actually being pulled by an invisible force called friction. Looking at the bottom right diagram, Galileo reasoned that if you removed all the slopes and all the friction, that blue marble would have absolutely no reason to slow down. It would keep rolling perfectly straight forever. A few decades later, Sir Isaac Newton took Galileo's observations and formalized them into 3 universal laws of motion. Motion isn't magic. From a falling apple to a playground game, everything follows a strict, invisible rulebook. The first law is all about stubbornness. Simply put, objects will resist any change to whatever they are currently doing. Look at these 2 side-by-side photos of a carom board. If you hit the bottom piece of a stack fast enough, the upper pieces don't move horizontally with it. Because those coins were at rest, they want to stay at rest, stubbornly hovering in place for a split second before dropping straight down. This stubbornness applies to movement too. When you are riding in a bus and the driver suddenly hits the brakes, your body gets thrown forward. The bus stopped, but your body, already in motion, stubbornly keeps going. We have a specific way to measure this stubbornness. We call it mass. Pushing a bicycle takes very little effort, but trying to push a car is exhausting. Because the car is heavier, it has far more mass, which means it puts up a much bigger fight when you try to change its state of rest. Newton's first law reveals the universe's tendency to maintain the status quo. Mass is just the exact measurement of how strongly an object fights back against being changed. So if everything naturally fights against changing its speed, what does it actually take to overcome that stubbornness and force something to move? The heavier the object, the harder you have to work. To get a heavy wooden crate up to a walking speed requires a substantially larger push than moving a cardboard box. You can feel this difference in an impact, too. Catching a light plastic badminton birdie is painless, but a dense cricket ball hitting your hand at that exact same speed will sting. This introduces a concept called momentum. Momentum is essentially mass in motion. It calculates the impact of an object by combining how heavy it is with how fast it is traveling. This chart shows Newton's second law, which gives us the exact mathematical recipe for motion, F equals ma. The force you need to apply equals the object's mass multiplied by the amount of acceleration you want to achieve. The second law provides the physical cost of doing business. To move a heavy object or to speed something up very quickly, you must pay for it with a bigger push. The third law introduces a fascinating boundary to all of this. Forces never exist by themselves. They only appear in pairs. This diagram illustrates the rule that every action has an equal and opposite reaction. Notice how the blue sphere pushing the red sphere creates an identical opposing push. The red sphere pushes right back. You use this invisible force pair every time you walk across a room. To take a step, your foot pushes backward against the pavement. Because forces always come in pairs, your backward push forces the earth to push you forward with the exact same amount of energy. The universe operates on a strict give and take. It is physically impossible to touch or push something without it pushing you back with the exact same strength. Let's bring it all together. First, objects are lazy. They want to keep doing exactly what they are already doing. Second, to force a change, you have to apply a push that scales directly with the object's mass and your desired speed. And third, every time you apply that push, the object pushes you in the opposite direction. These 3 rules govern every interaction you will ever have with the physical world, from the way satellites orbit the planet down to the way your chair is holding you up right now. Every move you make is a live demonstration of physics in action.